When we talk about optimizing, and if we are looking towards metaheuristics, we often get confused. And one of the reasons why we get confused is that there are so many algorithms. Literally, there are 500 plus or maybe more algorithms. Now, the thing is that, like, how are we going to make the choice that which algorithm is good? Right. We have heard about PSOs, whale optimization algorithm, then gray wolf optimizer, okay, seagull optimization algorithm, then ant colony, right? Ant mating, like there is, it's like endless. So we need a convenient method, convenient method to know that how we can make the judgment of picking up certain algorithm and putting it into our application use, right? So you can be coming from any industry, whether it can be logistics or computer science, or maybe if you talk about uh, like this metallurgy and all, okay, physical sciences and all, whatever. So we need, basically what we need is we need certain parameters for judgment. Okay, so I have identified certain methods, okay, like certain parameters by which we can see whether the algorithm that we are picking up, or suppose we are proposing certain algorithm, it is not the same algorithm that has already been proposed, okay, or we need to differentiate or make our algorithm unique. That is very important, right? So first of all, we need to understand that there are certain basic algorithms which were given long back, okay, long back, and many of the algorithms that we are proposing today, or we see, oftentimes we see in different research papers, okay, in academics, that is, these are nothing but it's like a, you can say like a, same wine in a different bottle. So this is not a good situation, right? This should not happen. So what we can do is that we can ask 6 questions. Okay, so we are going to ask, Six questions. Very important. Six questions. And if we are getting the answer to these six questions and the answers are different for two algorithms, it means those algorithms are different. Okay, so this six parameters of judgment, this is required. Okay, so the first question that we are going to ask, that is the question one, does the algorithm work with one solution or many? Okay, so some algorithms they work with a single solution and it keeps on improving it. Okay, it's like a person walking uphill. Okay, always moving to a better spot. So we call this as a single solution approach. Okay, so going uphill, that is um, single solution approach. Okay, and one of the very famous example classic is the simulated annealing. Okay, so one solution, one search path. Okay, and this is extensively used in the industries like, for example, say chip design, metallurgy. Basically, it is the motivation itself is coming from metallurgy. Okay, and it handles highly irregular search spaces. Okay, okay. So this is one thing. Okay, so on other types of algorithms, it often works with a whole population of solutions. Okay, another is this is the first one, and this second is the whole population of solution. For example, we are having swarm optimization, right? Swarm optimization is there, where what happens like there's a swarm of agents that is exploring a search space. Okay, a search space or a landscape. Fine. So this is one thing, and genetic algorithms they are also a part of this genetic algorithms. So what they do is that they maintain hundreds of candidate solutions in parallel, and um, they try to see that what are the options they are having. Okay, so uh, you can say that these kind of problems, like these kind of algorithms, are helpful in certain scenarios. For example, engineering issues. For example, aerospace engineering. Okay, so this question is very like important, and this is primary. Second question that we can ask is, what is the core movement or search operator? So kind of this is the heart of the algorithm. So if you strip away the nature metaphor, like sometimes it is after whales, sometimes it is after birds, sometimes it is after fishes, sometimes it is about certain kind of social behavior. If you strip away all these things, what is the actual equation that generates a new solution? So our focus here will be on the equation. Okay. For example, if we talk about PSO, particle swarm optimization, the particles they move based on their own best position and the swarm's best position, right? So it is a velocity equation. It is a velocity equation. So this is like the one of the thing that we can use case scenario is power systems or something. Okay. Um, for suppose load dispatch or grid optimization and all these things, like PSO really helps over there. Another is that very famous one is the ant colony optimization, where the ants they deposit certain kind of pheromones on the path, and the future ants they prefer a stronger pheromone trail. Okay, so again the movement is getting influenced. Fine. So this pheromone mechanism it naturally models the route preferences. Okay. So this is another thing that we have to see that what is the movement, like how is the movement happening, and we need to focus on the movement. Very important. Another question, that is the question number 3 that we need to ask, is that how is the exploration and exploitation these are balanced? Okay, how are these are balanced, how it is balanced, this is the thing, how these two are balanced. Okay, certain algorithms um, they have more emphasis on the exploration part, certain have more like more support for the exploitation. It depends. Okay, so different algorithms they handle this thing differently. Okay, for example, if you talk about the simulated annealing. Okay, what happens in this case? In this case, what happens, it starts very hot. Like the logic behind it is that in like a metallurgy process, it starts very hot. It starts very hot, and it accepts the bad solutions early on to explore widely. Okay, so explore early and widely. Then it cools down. It cools down. And then it becomes extremely selective. Okay. So the temperature schedule controls this balance. Okay, so it is useful for TSPs, okay, traveling salesman problem. Okay, because the early chaos, it helps escape the bad tools. That is the point actually. Okay, so the exploration, it happens very highly in the starting phase. But if you talk about the taboo search, very famous, another one, taboo search. It does the opposite. It does the opposite. It is exploitation dominant. It is exploitation dominant. Very important. So it always tries to move to the best neighbor. Okay, but it uses a forbidden list to force occasional exploration. Okay, so occasionally, occasional exploration. So basically, it is trying to exploit the solution. Okay, but Occasionally, it tries to explore also. Okay, so this is good for manufacturing. Suppose you're having the job scheduling, shop scheduling, all these things like manufacturing domain, it will have much more benefit if we talk about the taboo search. So many newer algorithms, if we see that are named after animals, they claim certain novel balance mechanisms. But if you examine their equations, it often reduces to the same inertia weight trick that the PSO, that is the PSO, introduced long back in 1995. Long back. Okay. So we can also think in this way. Then, if we talk about the fourth question, very important. Here we can actually, if we can implement this part, na, if we can work on this part, we will basically we'll have very nice options of hybridization. Okay, and very important for uh, publications and proposing newer solutions, and it's like a legit modification. Okay, that is that. Does it use memory? Very important. Does it use memory? Okay, and if yes, what kind? Okay, so kind also very important. This question is, I would say, one of the like for current times. This is one of the very important thing. Okay, so this is a very powerful differentiator. And if you talk about the memory in case of metaheuristics, either it is not using any memory, or it is using short-term memory, or it is using a long-term memory. So first of all, let us see the case of no memory, where what is the thing is that the algorithm has no record of where it has been. Okay, so each step that is taken, it is based only on the current state. For example, a random search. Okay, so many swarm algorithms like Grey Wolf, Whale optimization, Firefly, for all these things. Okay, Firefly, they all fall into this category. It is not remembering. Okay, so they can revisit the bad regions repeatedly without even knowing it. Okay. Another thing is that we are having the short-term memory. Like we are having certain memory for certain time we are keeping. Like for example, if we talk about the taboo. Okay. So it is one of the definitive example. So it maintains a list of recently visited solutions and forbids returning to them. Okay. So you have visited certain shop, and if you don't get the product that you need, so you might not immediately visit that shop. You might visit it later someday, but not the exact same day. Okay. So this is a very powerful for this is very powerful combinatorial scheduling problems. Okay, and it actively avoids cycling, where cycling is a big problem. So your algorithm is getting stuck somewhere, right? Another is a long-term memory. Now this is like, for example, if we talk about the ACO, if we talk about the ACO and colony optimization, what it happens, it builds a pheromone map over the entire run, right? Like we just talked. So it remembers statistically which part have been historically led to good solutions. Okay, so it intelligent, it remembers. Okay. Um, so what is the benefit of having the ACO, having the long-term memory? It improves with more iterations in a way that many memory-less algorithms do not. Okay, so there is the cycle problem is reduced, like it's like very less, almost negligible. Okay, and no memory, it can get stuck in cyclical issues, right? But here this issue will not be there. So this is a very good choice. Okay, and the thing is that for this is a very like PhD grade solution I'm giving. PhD grade solution, that is you add memory. You add memory. to a non-memory algorithm, or improve or increase the memory of the short-term memory. Okay, very important. Okay, the fifth question, that is the question 5 we are having. Okay, this is about what type of problem does it represent solutions for? What type of problem does it represent solution for? Okay, so we have different kinds of problems. Okay, so the problems that we are trying to solve using the meta heuristics of different industry. Okay, these are all of different types. For example, the problem classification, like if we talk about the problem, it can be a continuous problem, it can be discrete problems, it can be combinatorial problem, it can be multi-objective. For example, the problems, the I've taken out around 4 SCI research papers on this multi-objective problem, where we were trying to optimize the task scheduling problems in edge computing. So it was a multi-objective. Okay, so this is one of the scenario. Okay, so these things also we need to see. Okay, so just don't put a certain type of algorithm in certain scenarios. Like don't try to solve a problem for which it might not give a good answer anyways. Okay, so what happens is that for testing part, if you have lots of time, you can just test it out. But theoretically, as per like my analysis, it should not happen because it is not suiting, right? For example, if we talk about the continuous problems, so um, here we can have um, like if you are dealing with certain kind of turbine blade angle, like engineering problems. So in this case, what happens is that um, during the hyperparameters and all, so this is all have to do with the continuous problems. But if we talk about a discrete, okay, so when we have the binary choices, okay, for example, selecting certain features, very important for machine learning problems, right? So if you are optimizing the feature selection using the meta heuristic, you can go for here. Like for example, genetic algorithms with binary encoding and ACOs, they work very well. Okay. So if we talk about a combinatorial problem, here we are arranging or sequencing the things, okay, like TSPs and job scheduling. Okay. So supply chain routing, all these things are very like these are all combinatorial problem, and here also ACO will also work here in these cases. But apart from that, we have a taboo search and all these things will work. Regarding the multi-objective problem, suppose we have conflicting goals simultaneously. Okay, like we have to minimize certain cost, maximize the quality. Okay, so balancing with other fitness function variables and all. So for these things, here we need certain different kind of um, for example, NSGA to okay, all these things we can use for solving these kind of problems. In fact, I, in this case, proposed a hybridized version of Whale. Then Seagull, I proposed Coty optimization. This is another algorithm. Okay, so here we tweaked the inertia weight part. We applied genetic modifications. So basically, we all can use certain things in this kind of algorithms. Okay, so the point is that if suppose somebody comes to you and just says that. Suppose he gives you a routing problem and says that I'm going to use the Firefly algorithm. So you just like don't take it like just upfront. You see that because Firefly was meant for continuous problem solving. Okay, so now you are forcing the Firefly to work for combinatorial. Okay, so what happens is that either you make it adaptive in certain way. Okay, so make Firefly adaptive. Okay, adaptive for combinatorial problem. Okay, otherwise, just you're upfront applying. Otherwise, in a certain problem scenario, it might not work and it will waste a lot of time. Okay, then we have the final question. Okay, that is about the family. Okay, this all these algorithms they fall into certain kind of family. Okay, irrespective of what their name sounds, basically they all come from certain kind of families. For example, we have evolutionary algorithms. Okay, we have intelligence or optimization problems, swarm intelligence. We have differential evolution, simulated annealing, simulated annealing. Okay, then we have estimation of distribution and local search. So basically, all this will fall in uh, one of these families. Okay, so I hope this gives you certain insights. Okay, so this is one of the approach that I'm suggesting to go through these 6 questions and classify. So for a same use case, take 2 algorithms and ask these 6 questions and see that whether it is ultimately the same algorithm or not. If not, then what is the improvement scope that you have? And you can even you will get the hybridization uh, formats and all that. You can even make adaptive, like I said. All these things you can just apply. But before that, these basic 6 questions you ask. Okay, so I hope I'm clear. Any issues you can comment. Thank you.